All right, how's everybody today? Sounds good. Okay. Well, we're now in the third 6 weeks. Things are going to be happening pretty quick. We are starting the next lesson today over what we call error approximation. So the majority of the lesson is going to be looking at operations involving error. And then there's also quite a bit of other concepts kind of packed into this one particular lesson. Like time zones, interval notation, conversions of different measures, things of that nature. Hey, so we'll start this today. I'm thinking we'll go ahead and have ourselves like an exit ticket over part of this material tomorrow. Wednesday, I'm not going to be here because being IB students, you guys know that Wednesday and Thursday are what? Okay, those are going to be the CAS IB interviews. So I believe it is the seniors on Wednesday and the juniors on Thursday, correct? Okay, so I'm going to be on campus, but I just won't be in class. What I'm thinking that day is I'll go ahead and leave you an exit ticket to work on that covers the material you turned in today. We'll talk about it in just a minute. But probably go ahead and leave you the homework. I haven't decided if I'm going to leave you the assignment for this Wednesday or just go ahead and give it to you Thursday. Probably Wednesday, so because that exit ticket's not going to take the entire class period. And then we're going to get as far as we can this week. The next lesson after this, we're going to move into sequences and series, specifically arithmetic, but then what's happening next week. Remember, what did I say I was going to do? There you go. So starting next week, okay, just the 11th to the 15th, I believe are the correct dates. I'm just going to give you the class period each day. Chromebook will be available. If you just want to go ahead and, if you haven't already started writing your internal assessment, if you have any questions about the paper itself or your topic or any of the strategies, I'm just going to go ahead and give you that time because when's the rough draft due? It is due on the 12th of December. I know that still seems like a ways off, but if you really think about with the vacations we have, including this week, we're only 3 weeks away from the Thanksgiving break. And then as soon as we come back from that, we have 3 weeks until the Christmas break. And it's the second week after getting back from Thanksgiving that rough draft is going to be due. All right, so we've got 5 weeks until we get there. All right, so a lot of stuff's going to be happening. Okay, a lot of stuff I just mentioned. Any questions so far? Everybody have a good weekend? Okay. Well, let's go ahead and take a look. I believe I have this at the end here. Okay, were there any questions on the assignment? Yep. 5, 6, or 7 was on the back. So let's see here. 5 with the railings and the poles. Okay, let's go ahead and talk about this. Now, does anybody want to go ahead and share the answer they got for part B? From each pole, as many stair rails as possible are cut. What's the maximum number of stair rails that can be cut from one pole? I got 6. Okay, let's go ahead and kind of talk about how we got that. So starting at the beginning, did anybody else get 6? I think the other answer may have been 7, depending on what you did. But I ultimately chose 6 over 7, and I'll show you why. But stair railings of length 0.52 meters to the nearest centimeter are cut from poles of wood, which each measure 3.60 meters to the nearest centimeter. So part A says the range of possible lengths of the stair railings is 0.515 meters less than or equal to R less than 0.525 meters. Okay, so this is one of the things that we talked about last week. We know that the stair railings have 0.52 meters. Well, how'd they get this bound, the range right here? Does anybody remember what we did? Hey, John Henry.
You take one half of the smallest unit given, and then that accounts for your.
There you go. So to create that range, we're going to go ahead and add and subtract 1/2 of the smallest unit available, right? But this was a decimal value. In fact, how many decimal places do I have? 2. So we were going to go ahead and take 1/2 of 1 what? 1/100ths because we had 2 decimal places. Remember, if we look back in the notes, this was one of those unusual ideas. If it was a decimal, we had to take 1/2 of 1/10 if it was one decimal place, 1/100 if it was 2. If it was 3, we would do what? Take 1/1000. So half of 100, that's 1/200, which is 0.005. Okay, so for example, 0.52 plus 0.005, that's our 0.525. The 0.52 minus 0.005, well, there's the 0.515. So what they're wanting us to do is the exact same thing, but for the poles. Okay, now the poles, we're told, are 3.60. So again, we have 2 decimal places. So I'm going to do the same thing. I want to go ahead and add and subtract 0.005 to that value right there, the 3.60. All right, well, we're talking about poles here. All right, so let's go ahead and do the upper one first. So what's 3.60 plus 0.005? $3.605. And then let's go ahead and take 3.60 minus 0.005. 3.595. There we go. Okay, so there's my range of possible values for the poles. Is everybody okay with that? Okay. Now we get to part B. From each pole, as many stair rails as possible are cut. What's the maximum number of stair rails that can be cut from one pole? So how I looked at this, I went ahead and took the smallest pole, and I went ahead and divided it by the biggest rail. Okay, so what's the length of the smallest pole? 3.595. 3.595 divided by. Now here's the thing. If I go ahead and take the largest rail, okay, which they're giving me right here as 0.525, we don't want to go ahead and use that value itself because, remember, it's not included. So we can go just below it. Let's go ahead and choose a value that's within that range. I went ahead and chose 0.524. Okay. So I took the length of the smallest pole and the largest rail in order to get the maximum number of rails that we could have out of this. Okay, so if I go ahead and take that, 3.595. Did I make a mistake? Actually, I did it another way as well. I also took it with the largest pole and divided it by the smallest rail.
That's how I did it, because I figured you would want the smallest number of things.
Yeah, so let me show you why I ended up doing this the way I did. Okay, so 3.595, let me get rid of all that trig. 3.595 divided by, what do we have here? It was 0.525. Is that right? 0.524, that's right. I didn't want to include that. Delete 4. Okay, so it's going to give me 6.86. So now normally when we see that large decimal, we want to go ahead and round up, but we're talking about lengths of these railings, right? So I only got a portion of a railing. I can't round up and say that I got 7. So I'm only able to get 6 out of this one. Is everybody okay? All right, so we're able to get 6 railings. Okay. And then the same thing here. If I do go ahead and switch it around, I tried it the other way. If I take the largest pole and I go ahead and now divide it by the smallest rail. Okay. All right. Well, the largest pole was 3.605, but I can't include that. So what would be a value just immediately prior to it? 3.604. Okay, divided by. I just want to keep that in mind, because we can't include that upper value. And then the smallest rail we can include, which was a 0.515. Okay. Now, if I go ahead and divide those, 3.604 divided by, I think it was 0.515. Okay. See, we get even a larger decimal here. So 6.99. You would want to go ahead and round that up, but you're not quite getting that full unit. So again, I got to go with 6 railings. Okay, so either way, you go ahead and take a look at it.
Is there a way that's better whenever we're solving these?
I actually went to Mr. Reeves on that one because I wanted to double check that I was getting the right answer, and he couldn't think of another method. He agrees that the 6 is correct. So.
Well, yeah, but is it better to divide like the largest by the smallest?
You know, originally what I did, I took the smallest pole and divided it by the biggest rail.
So if we do
That's what I did. Because if we're looking for the maximum number of rails, I wanted to go ahead and divide by the longest rails possible.
aren't the
That's my
rails
thought.
cut from the poles?
Yes. But see, even if we reverse it the other way, it's pretty much identical to each other. It's just that it has a larger
So it should,
decimal here. Shouldn't be that horrible. Yeah, shouldn't be that significant. How many people worked that problem and did get 6? Okay, good. Did you work it another way, or what'd you do?
I did it the second week.
Okay, the second way. Okay. Who had their hand up over here? Okay, Ethan, what'd you do? Top one. Okay. All right. And Bella, you asked about that one, right? Does that make sense? Okay. All right. Was there anything else? Number 6. Okay, so what do we got here? A 2,000 meter to the nearest meter length of fiber optic cable has a radius of 3.45 times 10 to the negative 5 meters. Find the volume of the cable. Be sure to use appropriate units. Okay, well, let's think. We're talking about a cable, but realistically, I mean, this is what kind of figure? Yeah, it's going to be a cylinder, right? So if I'm talking about finding the volume of the cylinder, like let's say this represents a very enlarged portion of this cable here, so I am not an artist by any means necessary. So this radius is 3.45 times 10 to the negative 5 meters. Okay, so the idea is if you're dealing with a standard cylinder, you want to find the area of the base times the what? Times the height. Okay, so the area of the base is a circle, so we know that's going to be pi what? Radius squared times the height. Well, in this case, the height is just going to be the length of the cable that we're dealing with. Okay, so the volume is going to be pi times the radius squared, 3.45 times 10 to the negative 5 meters squared. And then we want to go ahead and multiply that by the 2,000 meter length. Double one. Hello. Oh, hey. There you go. There you go, man. Okay, and now it's just a matter of seeing what that calculates out to. So I'm going to use pi times, I believe it was 3.45 times 10 to the power of negative 5. And, you know, that's not a very large number to deal with. You probably could just go ahead and move the decimal over 4 decimal places, but I just went ahead and typed it in as a scientific notation. And then we wanted to multiply that by 2,000. There we go. Okay, so as soon as I go ahead and push enter, okay. Now, oh, did I forget something? Oh, damn it. Hang on. I knew I forgot something. I was like, that's not what I got. Okay, so let me go back over here. Oops, okay, so let's put a parentheses right there. Let's go ahead and put a parentheses right there. Let's square that. There we go. That ought to come out nicely. Okay. And then if we want to actually see, because your calculator is most likely going to do what mine does, depending on the settings, it'll go beyond that. Okay. So in fact, when I highlighted it and put it here, it went ahead and wrote it out in scientific notation. That's what the E stands for on the Inspire, the capital E. Because remember, the way they want it written in IB is that the value of A is always going to be between 1 and 10, 1 included, and it's going to be times 10 to the K, where K is a what? Starts with an I. Integer. It's going to be an integer value. So in this case here, what do we end up with? 7 point, let's say 48. Okay. So 7.48 times 10, and I believe that was negative 6. Now this is meters, what? Cubed. Cubic meters. Okay. Joey? Is that good? All righty. Anything else? Okay, then we'll go ahead, move on. The people who weren't here on Friday, did you get my remind message about the assignment? Okay, so even though I did send that out, because you weren't here on Friday, if you go ahead and get this to me tomorrow, I'll still go ahead and put those points in the point bank for you. We'll go ahead and start that for the third 6 weeks. Okay. All right, well, let's switch gears a little bit here. We're going to go ahead and start talking about error approximation. And we're going to be performing calculations with errors. So parts of this are going to be a little unusual, especially the bottom of this first page right here. Okay, so what are we talking about? Assume absolute error to be the smallest unit of measurement at your disposal. For example, measuring with a ruler, the smallest unit is 1 millimeter, so your measurement is accurate to plus or minus 1 millimeter. Relative error tells you how far off you were in comparison to the real measurement. Okay, so we're going to be dealing with absolute error, relative error, and percentage error. In order to find these three, okay, you first have to find absolute error, which you use to find relative error. Then you use relative error to find your percentage. In fact, the only difference between relative error and percentage error is that you just multiply the relative by 100 to move the decimal over and you have a percentage. That's the only thing there is. Okay. Now, I got a simple little example to go ahead and get it started right here. It says you see 2 trees off in the distance. You estimate the distance between them to be 18 feet. The exact distance between them turns out to be 20 feet. What are the absolute, relative, and percentage errors? Okay, well, we have these formulas here, and this is going to be provided in your formula book, so it's not one of those that you have to go ahead and commit to memory. But you'll notice here, absolute error is the absolute value of V sub A minus V sub E. Okay, so V sub A, that's the approximated value. That's what you believe it to be. V sub E, that's what it truly is. That's the exact value. So in this case right here, AE stands for the absolute error. I see 2 trees in the distance. I believe they're 18 feet apart. So that would represent what? V sub A or V sub E? Okay, so this is V sub A. Now in reality, it turns out they are 20 feet apart. So this is my V sub E. They are exactly 20 feet apart. So if I want to go ahead and find the absolute error, I'm going to take the absolute value of what I believed it to be minus the actual distance, the exact one. And remember, what does absolute value do? Yeah, it's going to make it positive. You're talking about the distance from 0 on the number line. Okay, so this is just 2. All right. Well, now I want to go ahead and find relative error. As it says before, this tells you how far off you were in comparison to the real measurement. So basically, this is going to set up what your percentage error is going to be. So I'm going to go ahead and take V sub A minus V sub E, okay, what I just found, the 2, and I'm going to go ahead and divide it by the exact. Okay. Oh, no, I'm sorry, the exact value, which is 20. So this is going to give me 1/10, which is 0.1. So that would be the relative error. Okay. So as I mentioned, what do you got to do now to the relative if I want to find the percentage? Yeah, just multiply by 100. So I'm going to go ahead and put PE right here, percentage error, 0.1 times 100. Well, we're looking at 10%. So with this problem right here, how much in error was I with my estimation versus reality? Oh, I was 10% off. That's what we're talking about. Does that make sense? Does anybody have any questions on that? Ooh, we're very quiet today. Is it a Monday? But you're in math class, so you're your favorite class, right? Absolutely. Joey, good man. Okay. All right. Oh, I erased that. Let me erase that right there. Okay. Okay, so let's try this one. If the fraction 7/5 is used to approximate the square root of 2, what are the absolute, relative, and percentage errors associated with this approximation? Okay, well, let's go ahead and start with the decimal value here. Let's just kind of get an idea. What is 7/5 as a decimal? It is 1.4, 1 and 2/5. Okay, so 1.4. Now, we're going to go ahead and plug this fraction and this radical into the calculator in just a moment, but I just kind of want to get a feel for what we're doing. Now, what is the exact value of the square root of 2? Does anybody know it to like 3 sig figs off the top of their head? Is that one you're accustomed to? 1 point something. 1.41. Now, John Henry, did you know that off the top of your head, or did you put it in the calculator? Say off the top of your head. That's amazing. All right. So it is roughly like 1.41, and it just keeps going. That is an irrational number. It's real, but it's irrational. Okay, so let's go ahead and find the absolute error. So I'm going to go ahead and take the absolute value of what I believe it to be, 7/5. We think that's a pretty good approximation, minus the exact value. Well, because this is irrational, we can just go ahead and plug in the square root of 2 itself. All right, so let's see here. Come on over here. Let me go ahead and get rid of all this. So absolute value, if you go ahead and click this button right here between 9 and the open catalog, remember where we went in for our matrices? Absolute value is the second row, first icon right here. Okay, there we go. So now I'm going to type in 7/5, 7/5, minus the square root of 2. All right, so I'm going to go ahead and push enter. So I'm getting an absolute error of 0.014214. Okay. I'm sorry? Oh, absolute value. Let me go back again. If you hit this button right here between 9 and your catalog, right below delete, you get all these different icons. It's the second row, first icon. Okay. There we go. So let's go ahead and say this is 0.014, just to, write it in a certain number of sig figs and write it on my paper. So 0.014. Even though when I go ahead and move on to go ahead and find the relative error, I'm going to use the exact value in the calculator, not this rounded version. Okay, so for relative error, I'm going to take that difference, okay, the 0.014 that I just found, and I'm going to divide it by the exact value. So here, I'm just going to go ahead and say the square root of 2. Remember, because it's irrational, so it has an infinite number of decimal places. But doing it like this will definitely give me a better answer. So, control divide. Let me go ahead, highlight that one. Divide it by the square root of 2. Okay. So when I go ahead and push enter, 0.010051. Okay. So I would say 0.010. Okay, if I'm just going to go ahead and stick with 3 sig figs. All right. And then now what do I need to do in order to find the percentage error that we have here? Multiply by 100. Okay, but that's all that's going to do is move the decimal over, but I'm just going to go ahead and do it anyway. Okay, so let's say 1.01%. Okay. There you go. So not a very high percent. I mean, a lot of people do tend to use that. In fact, does anybody know what fractional value they use to approximate pi? Anybody remember that ratio? Maybe you were taught it in Algebra 1. Does this look familiar? 22/7. Okay. Would anybody? This isn't part of the notes. It's just another example that I thought of because 7/5 compared to square root of 2. Did you want to go ahead and figure out what the percentage error is of using the fraction as opposed to the actual pi value?
Yeah.
You want to go ahead and do that? Okay. Well, let's do it. Would anybody like to come on up here and help me with this? Oh, it suddenly got really quiet. I don't understand. Okay. Well, let me go ahead and erase this again. So now we're going to compare 22/7 to pi. Okay. So who wants to come on up and help me? Whoa. Too many hands. I only need one.
Random number generator.
You want me to do the random number generator? Okay. I'll just use the calculator. I know it's not the most efficient, but it'll just make things go a lot faster. Huh?
No.
Document B. Oh, Reese, are you volunteering?
What? No.
What?
No.
Oh, okay. I heard you talking. Okay, so probability, random, integer. I want one person out of, I'll go ahead and put the full 36 in here. Why not? Okay, now the first one on the calculator, it always gives me 34, right? So I'm going to go ahead and go with the second one. 14. Joey! You are 11, yes. All right. Okay, so Joey, how do we find absolute error?
The absolute value, the absolute,
Okay,
right? So is it 22 over 7?
yes. 22 sevenths minus pi. Okay, now let's go ahead and see what we get here. Let me go ahead and document B. I'll go ahead and take out the calculator for you. So control divide, so 22 over 7 minus, okay. Okay, so 0.001264, so let's say 3 sig figs on that. What would that be, Joey?
0, 0, 1, 2, and then 6.
There you go, 0.00126. Okay. Now again, I'm just rounding it to 3 sig figs to have something on my paper to kind of show my work. I mean, we're going to be using that to calculate the next one, the relative error. So now I would take that absolute error and divide it by what?
This one right here? Or this one?
That's a good question.
This one.
Okay, so we take the absolute error, that's true.
And then
Now would I divide by 22 sevenths or pi?
divide by pi.
We always divide by the exact value. Okay, so let's write that ratio. So 0.000126 divided by pi. Okay, so here we go. Oh, there's only 2 zeros, I'm sorry. All right, so we'll fix that in a second. So now I'm going to go ahead and divide that by pi. Okay, so now it's 0.000402. Okay, so why don't you go ahead. Let's write that down. 0.000402. And let's go ahead and fix this real fast. There we go. All right. And now what do I do in order to find percentage error from relative error?
Multiply by 100.
Just multiply by 100 times 100. Okay. So let's round that to 3 sig figs too. Why not? 0.040%. Okay. There we go. That's all there is to it. So that's a really low percentage, right? I mean, there is a little bit of error, but it's definitely not too terrible. Okay. So has anybody ever seen that 22 sevenths before? Some of your teachers have probably had you use that in place of pi. Okay. All right. Good, 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 good. All right. That is absolute, relative, and percentage. Is everybody kind of starting to get the idea?
We had to kind of do it.
Oh, good, good, good. Is anybody confused? You're less confused. All right. Well, there we go. Okay. Well, let's go ahead and look at computation errors. Whenever calculating with one or more quantities that are in error, the results will also be in error. This is often true in measurements because we can only be so accurate when taking them. Okay, so example, a rectangular field has been measured as being 120 meters long by 55 meters wide. Both measurements are correct to 2 significant figures. What are the bounds on the errors if these figures are used to calculate the perimeter and then the area? Okay, so my final answer, we're looking for the range of values, the boundaries. So not an exact number like we did in the previous lesson. Okay, so there was something we used on this. Remember, it was 1/2 plus or minus 1/2, the smallest unit of measurement. We were working with that on the previous one. So let's go ahead and apply that to the perimeter here. So for the length, okay, we've got 120 meters. So let's go ahead and put the length right here in the middle. Okay. So we're going to go ahead and add and subtract 1/2 of a meter. So what would the upper value be? 120 plus 1/2 a meter. 120.5. Okay. And then 119.5, because that's 120 minus 1/2 a meter. Yes, sir.
So the measurements being correct is two sig figs doesn't.
And see, here's the thing. Our final answer, we are going to go ahead and make sure that it is, the boundaries are in 2 sig figs, because the problem made specific mention, both measurements are correct to 2 significant figures. But we don't have to do that right now, because we're going to go ahead and use this to help get that final answer.
So we
All
just
right.
have to go.
Yeah. In fact, typically, unless it's stated specifically like this one is, that really doesn't apply to the boundary answers that we were looking at last time. Okay. Now let's go ahead and do the width. Okay, so the width was 55 meters wide. So what would the upper boundary be? Emma?
55.
55.5. Okay. And the lower boundary, Jacob? 54.5. There you go. 4.5. There we go. Okay. Now, what do we go ahead and do to figure out the perimeter? If we have the boundaries for the length and the width. We're going to take the 2 lowest ones together. Then we're going to take the 2 highest together. Okay. So I'm going to go ahead and say, because the perimeter is always 2 times the length plus 2 times the width. Okay. So 2 times 119.5 plus 2 times 54.5 is equal to, somebody help me out with that. I believe it's in the 300s. 348? Okay. All right. Now we're going to do the same thing with the upper values. 2 times 120.5 plus 2 times 55.5 equals 300. Oh, I heard someone say it. 352. Okay. So now here's where this one's getting kind of unusual. I think this one's the exception, because what we would go ahead and do now is say, okay, well, the perimeter is going to go ahead and be between 348, okay, and 352. Now, because the problem did make sure to go ahead and say both measurements are correct to 2 significant figures, we would go ahead and make sure that this final boundary here is going to be in 2 sig figs as well. But does anybody notice it? Yeah, 348 in 2 sig figs is 350. 352 in 2 sig figs is 350. Now, honestly, I don't know if IB would want you to go ahead and write out for a problem like this, 350 is less than or equal to the perimeter less than 350. I wouldn't, because for me that just seems kind of ridiculous. I would go ahead and say either 350 or leave it like this. Again, this is another problem I went and asked Mr. Reeves about, and he said he would probably, even though it says it wants the bounds, he would probably just go ahead and put 350 as a final answer because of the sig fig portion. Okay. All right, question. Good. Okay. Do we want to try one on our own? Sure. Okay. All right. Whoever said that's awesome. It's just so quiet today. This class is never this quiet. You're just absorbing all the information. There you go. Okay. All right. Okay, so what are the bounds on the errors if these figures are used to calculate the area of the field? So you're going to do the same thing. We need to go ahead and find the bounds for both the length and the width, again, but basically what we just had, and then you're going to go ahead and use those to help you figure out the area. All right, so let me go ahead and write these out again because I erased them. So for the length, okay, we had length equal to, what was that, 120, so that's 120.5, and this one right here is 19.5. It was 55. Hmm?
Secrets over there.
They're telling secrets over there.
Mm-hmm.
I mean, is it really a secret when you're telling somebody math is awesome? I mean, what is that? That's his pen? That's not doing anything. There we go. The singing pen. Does not want to sing for me. That's all right. All right. Okay, now I'm not going to go ahead and give you the actual products. I'm going to go ahead and give you what I got for the bounds after I wrote them as 2 sig figs. I got it to be between 6,500 and 6,700.
We think this.
Okay. Because what I did was I took the lower boundaries, I multiplied those together, and I ended up with 6,512.75. Okay. Then I multiplied the uppers together. I got 6,687.75, and then I just put those bounds in 2 sig figs. Okay. How many people got that right? Woohoo! All right. Any questions? Okay. Here's where it's going to get unusual. Okay. If you have values where you're already provided the error, okay, there are certain rules for performing multiplications on these. So if you have a value that looks like this, like 5.3 plus or minus 0.1, that plus or minus value, that's your absolute error. That's your absolute error. Okay. So kind of think about, the first problem we did with the trees. You remember how I thought they were 18 feet apart. They turned out to be 20, so the absolute error was 2. So it'd kind of be thinking about 20 plus or minus 2. Okay, so I was within 2 feet of actually guessing the correct distance between them. All right. So here's the thing. If you were just going to add or subtract these type of values, it is very, very simple. But the one rule, always add the errors regardless of whether the other numbers are added or subtracted. So every time you add or subtract values like these, you always, always add the errors. So take a look at A. I want to take y minus z. So y is 12.2 plus or minus 0.1. And I want to subtract z, which is 5.6 plus or minus 0.1. Okay, well, you still go ahead and take the original number, the value. You go ahead and subtract those just like normal. So somebody help me out. What's 12.2 minus 5.6? $6.6. There we go. Okay. So those exact values, you go ahead and just perform the normal operation with them. 12.2 minus 5.6 is 6.6. But whether you are adding or subtracting, it does not matter. You always add the absolute errors. So what's a 0.1 plus 0.1? 0.2. That's it. Boom. Math. There we go. That's all there is to it. Simple. Okay, now when you multiply or divide, that becomes a little more involved because you have to incorporate the relative error. Okay, so let's run through one of these. Maybe we can get through one before we get out of here. So I want to take y and divide it by z minus x. Well, if you're going to simplify the fraction as a whole, you can't do that until you simplify both the numerator and the denominator. So the first thing I need to take care of is z minus x. Okay, so I need z, 5.6, plus or minus 0.1, and I want to subtract x, which is 5.3, and then I'm going to add or subtract 0.1. Put parentheses in the wrong place. There we go. All right, so why don't you go ahead and take a few seconds to figure that one out for me. 5.6 plus or minus 0.1 minus 5.3 plus or minus 0.1. Okay, now the main values, you go ahead and apply the operation to them directly. What's 5.6 minus 5.3? 0.3, right? Plus or minus. Now, if you're adding or subtracting these error values, you always add up the errors, the absolute errors. So this again would just be plus or minus 0.2. Is everybody okay with that? Okay. So now, what we're going to go ahead and do, I'm going to take y, which is 12.2. Let me give myself a little bit of room down here. Okay, so now I want to take y, which is 12.2, plus or minus 0.1, and I want to divide it by z minus x, which we just found to be 0.3, plus or minus 0.2. Okay. All right, now, you remember what I said before? The exact values, you always just go ahead and apply the operation to them directly. So what I want to go ahead and do is take 12.2 and divide it by 0.3. All right, so I'm going to plug that in the calculator. 12.2, let me get rid of all this right here. 12.2 divided by 0.3. And I'm getting 40.6 repeating. Okay, so let's say to 3 sig figs, I'm going to say 40.7. So that is already part of my final answer. All I did was apply the operation to those exact values directly. But now, in order to find the error that goes along with this, what I got to do is find the relative and then take the percentage of that value. Okay, so let me walk backwards and tell you what I'm talking about. For the y value, the 12.2 plus or minus 0.1, I'm going to take the absolute error and I'm going to divide it by the exact value. Remember, that value that we're adding or subtracting, that's the absolute error. Okay, the value that we have here, the 12.2, that's the exact value. So I'm going to find the relative. So I need to know what this is. 0.1 divided by 12.2. 0.1 divided by 12.2. All right, so I'm going to get 0.00819. Okay, so let's go ahead and say 0.00820. I'm just going to go ahead and round that to 3 significant figures. Okay. Now I'm going to go ahead and do the same thing for the bottom value, the number that I want to divide it by. So I'm going to take 0.2, the absolute error, and I'm going to divide it by the exact value, 0.3. Okay. Well, this one you probably already know just by, recognizing that ratio, but I'm going to go ahead 0.2 divided by 0.3. Okay, it's just 0.666 repeating. So I'm going to go ahead and say 0.667. Okay. Now, everybody okay with what I've done so far? I found the relative error for each of the two numbers. Is everybody okay? Well, I'm going to add those relative errors up. Okay, so I'm going to take this one right here plus the previous one. Okay, and it's going to give me, like, let's say 0.6748. So let's say 0.675. Okay, this is the percentage that I need to go ahead and take of that original value. That's going to be my error. Okay. Now you notice I didn't bother multiplying it by 100 because if I need to go ahead and find the percentage of something, I got to write it as what? Like if I wanted to take 21%, what would I have to do? I'm not going to multiply by 21. I'm going to multiply by 0.21. So I'm not worried about the percentage error. I'm just going to leave the decimal right where it is. So this is the percent, basically 67.5% of this number right here. Oh, I added the two relative errors together. I took the sum of the two relative errors. So now I want to take that. Now remember, I rounded mine. Whoop. Okay, so hold on one second. Times. Now let me go back up here. There we go. Oh, so close. Here's the number that I originally got. So I'm getting 27.4. So plus or minus 27.4. That would be one error divided by another. Okay. Now, we'll go ahead and continue this tomorrow. But this relative error, basically think of that as the 67.5%. That's the percentage I took of the original calculation.
So it's when you're dividing something that makes the error like that. Right.
Yes. All right. Okay, we will continue this tomorrow. Okay, guys, thank you very much. You have yourself a great